Hello. In the last lecture, we have seen that fundamental group of a closed orientable surface of genus equal to 2 is a subgroup of PSU11, which is again a subgroup of the isometric group of the unit disk model of the hyperbolic plane. So in this lecture, we'll further continue the discussion and we'll prove that. So if you take a closed orientable surface of genus equal to 2, it admits a hyperbolic metric. So let us begin. Let us recall, so what we have done in the last class. So we have taken a geodesic regular octagon in the unit disk model of the hyperbolic plane. So this is my unit test. So we have taken this geodesic octagon such that the internal angle is equal to pi by 4. So all these angles are my pi by 4. And so then we got isometries. A1, which will take this red geodesic to the red geodesic. We got isometries A2, again B1, B2. So this A2, it will take, let us take A2 to be this hyperbolic isometry, which will take the black geodesic to black geodesic, and B1, it will take this blue geodesic to blue geodesic. And at last, we have another isometry, hyperbolic isometry, which will take this green geodesic to another green geodesic. So we have the side pairings. So the fundamental group of this genus 2 surface is generated by this A1, A2, B1, B2. So this will be a finitely generated group, and also it is a finitely represented group. So it is in fact, it is a one related group. So if I do this identification with the help of this isometries, so as a quotient, so you'll get this genus 2 surface. Okay, so now what you can do, so why this fundamental group is a quotient group, so that you can see from here. Yeah, so why this is a quotient group? So let us take, so let F be this regular octagon. So this is a closed region. So yeah, so what is this F? So this is by F. So this is this octagon, and take the interior of this octagon also. And the claim is, so this F is a fundamental domain. So first of all, note that if I apply A1 on this F, so if I apply A1 on this F, so it will go to another octagon. So it will be like this here. So it will go to another octagon. And now if I apply A2 on this F, so if I apply A2 on this F, so it will go to another octagon. And you keep on doing this thing. So you take any element G from this pi1 of sigma 2, and let us take G to be non-identity, and you take G of this F. So first of all, note that union of all this GF, where G is varying in this fundamental domain. So this is equal to whole of this disk. So we have a 8-8 tiling of this disk. So what do you mean by this 8-8 tiling? So this term I have used earlier also. So 8-8 tiling means, so 8, it represents 1-8, the first coordinate, it represents the octagon, this regular octagon. And the second coordinate 8, it represents the following thing. So if I take any vertex of this octagon, so you can see that 8 geodesics are emerging from this point. So 8 geodesics emerging from a vertex of the octagon. So around any vertex, in fact, so there are this 8 octagons. So if I consider this one, so this is one octagon, this is another octagon, this is another octagon. So 1, 2, 3, 4, 5, 6, 7, 8. So around each point, so there are 8 octagons. Okay, so we have a nice styling of this unit disk here. And also note that this F, it is a fundamental domain. Why? So first of all, this union of all this GF, it is equal to this this unit disk. And now if I take any point, let us take any point here. Let us call this point to be X. And if I apply some AI or some product of this A1, A2, B1, B2, so it will land in some other octagon. So this point, it will be my GX. Yeah, so let me write this thing. So if I take any G which is not equal to identity in this fundamental group of genus to surface, so G of this interior of F intersection interior of F is empty. So this is true for all non-identity element. So therefore, so this F, it is a fundamental domain. So we got hold of a fundamental domain, and this interior F, so it is an open set containing the point X. So if I take any point, okay, so let me write in this way. So let X belongs to this unit disk, and suppose suppose let us take x belongs to some translate of this interior of f. So this itself, so this is an open set containing this x, and now if I take any other g prime which is not equal to g, so then so g prime of this interior of f intersection g of interior of f, so this intersection will be empty. So therefore, what this will imply that so pi 1 of sigma 2 acts on D2 as a covering space action. So in fact, one can also prove that. So check that pi 1 of sigma 2 acts properly discontinuously on this unit disk. Yeah, so from the picture it is clear, this pi 1 of sigma 2, so it is acting on the space and the quotient space, so this will be homeomorphic to your sigma 2, and we have a covering map P from this unit disk to this genus 2 surface. So we have a covering map pi from this unit disk model to your quotient space, which is nothing but, again, the quotient space is nothing but homeomorphic to sigma 2. So in fact, this idea you can extend for any closed orientable surface of genus G where G is greater than or equals to 2. So let me write down that thing as a theorem. So this is mainly due to Poincaré. So let G greater than or equals to 2 and sigma G be a closed orientable surface of genus G. So then, so this pi 1 of sigma G acts on this unit disk with hyperbolic metric freely and properly discontinuously. So freely means it does not have any fixed points. So once you prove that it has a covering space action, so then automatically the action is also free action. So hence, pi 1 of sigma G is a quotient group. So you can refer to this book by Katok. The title of the book is Quotient Group. Yeah. Okay. So now how to get a hyperbolic metric on this genus G surface where G is greater than or equals to 2. So again, let me write down. So sigma g, so again, it is homeomorphic to this quotient space. And we have a covering map. So P is a covering map from this unit disk to this quotient space, which is just homeomorphic to sigma g. So in fact, so again, this, because pi1 of sigma g, it acts by isometries on this unit disk, and the isometries are differentiable maps. So therefore, sigma g, it will be a differentiable manifold, and in fact, this P, it is a differentiable map, and because P is a covering map, P is a local homeomorphism. So in fact, P is also a local diffeomorphism. So that means that the restriction map of P on an open set, on a suitable open set, it will be a diffeomorphism onto its image. Okay, so now because the speed is a differentiable map, now let us take some point in this unit disk. So we have the differential of this map. So this differential of this map, it goes from this tangent space of this T2 to the tangent space of the surface at the point Px. So again, note that, so this surface is nothing but T2 mod pi1 of sigma g. So this is a differential map, is the differential of P at x. Okay, so again, so this tangent space of this disk is just R2, and tangent space of, so this sigma g, it is a surface, so the tangent space, it is R2. So in fact, so this so P is a local diffeomorphism, so this will imply that, so this is an isomorphism. Okay, so this differential, so it is a map from this tangent space of disk to the tangent space of the surface. So now what do we want? So we want an inner product on the tangent space of the surface, which is isometric to the hyperbolic inner product on the tangent space of the disk with the hyperbolic metric. Okay, so now what we'll do, so let us take two elements, B star, W star, from the tangent space of the sigma g. So then, because this, so dxp is surjective, so this will imply that there exists BW in the tangent space of this unit disk at the point x, such that so this differential will take B to B star and W to W star. Okay. And now what is the definition? So definition of this inner product. So this is defined to be, so let us take this y to be equal to your px. So first I'll take some y belongs to sigma g. Again, P is a surjective map. So we'll get some x as that px equals to y. Yeah. So this inner product, so this is my definition. So this is defined to be the inner product of v and w at the point x. So this is the hyperbolic. So this inner product is the hyperbolic inner product defined on the unit disk. Yeah. So now again, so why this definition is well defined? So this definition is well defined. So by that, what I mean, so you can get 2 points x and x prime such that p of x equal to y and p of x prime equal to y. So let x prime belongs to this unit disk such that px equal to y equal to px prime. So this will imply that, so this will imply that, so there exists some w belongs to your pi 1 of sigma 2 such that fw x is equal to x prime. Yeah, so w belongs to pi 1 of sigma 2, so w will correspond to some isometry that I have called to be fw. So where this fw is the isometry of this unit disk with hyperbolic metric corresponding to w. Yeah. So this comes from this text transformation. So we have this diagram here. So here we have x, and here we have this x prime, and this map is p, and the other covering map is also p. So p of x is equal to px prime. So px equal to y equal to px prime. And so this unit disk, so this is a universal cover of this sigma g. So I'll have a disk transformation from this disk to disk, which will take this x to x prime, and the disk diagram will commute. So that disk transformation, in fact, it will be the hyperbolic isometry. So in fact, it will be that isometry of this unit disk taking x to x prime. So this diagram will commute. Okay, so because of this thing, so now if I take differential of fw at the point x, so this will be from this tangent space of unit disk at the point x to the tangent space of this unit disk at the point fwx. So w, so this is an isometry. So this will imply that so dfw will preserve the inner product. So therefore, uh, this definition is well defined. So therefore, the definition of inner product defined on sigma g is well defined. And clearly, so because of because of this, so this inner product defined on the tangent space of this sigma g, so this is isometric to the inner product defined on the unit disk. So in fact, you can check that this P, it is a local isometry. And therefore, so we have a hyperbolic metric. So what we have proved that, so sigma g, it admits a hyperbolic metric. Admits a hyperbolic metric. And if you know something about the computation of the curvature, so given this hyperbolic metric on this unit disk, the curvature at each point is -1. And this map P, from the covering map from P from this unit disk to this genus G surface, this is a local isometry. So therefore, the curvature at each point of this sigma G with respect to the hyperbolic metric, it will be also -1. So if I take any closed orientable surface of genus greater than equals to 2, so you can have a metric such that the curvature at each point is -1. Okay, so I'll stop here.